In 1916, just a year after Albert Einstein published his theory of general relativity, a German physicist named Karl Schwarzschild sent him a letter, not with praise, but with a puzzle. Schwarzschild had discovered something strange in Einstein's equations, a solution where gravity becomes so intense that space and time themselves break down. Einstein thought it was just a mathematical curiosity. Over a century later, we know it by a much darker name, the black hole. Black holes have since become the poster child of cosmic mystery. They're the villains in science fiction movies, the darlings of physics lectures, and the nightmares of spacecraft engineers. But here's the real question. What are black holes exactly? Are they giant vacuum cleaners, cosmic death traps, gateways to other dimensions? To understand black holes, we need to start with stars. Stars, like our sun, are massive spheres of gas, constantly balancing two competing forces. On the one hand, gravity is pulling everything inward, trying to crush the star under its own weight. On the other hand, nuclear fusion in the star's core pushes outward, producing light, heat, and stability. But this cosmic tug-of-war doesn't last forever. When a very massive star, at least 20 times the mass of the Sun, runs out of nuclear fuel, the outward pressure fades. Gravity wins. And what happens next is a collapse so extreme, it's as if the star folds in on itself like a crumpled soda can, only much more violently. In the most extreme cases, that collapse continues until all the mass is squeezed into a single point with no volume and almost infinite density. This is called a singularity, the heart of a black hole. Surrounding that singularity is the event horizon, the infamous boundary of a black hole. Cross it, and there's no coming back. Not because you'll crash into anything, but because space and time are so warped that all possible paths point inward. It's a bit like a cosmic waterfall. Imagine floating in a canoe toward a massive waterfall. From far away, you can paddle back with ease, get closer, and the current pulls stronger. Cross a certain point, the edge of the waterfall, and no amount of paddling can save you. You're going over. The event horizon is that invisible edge. Light itself can't escape this gravitational pull, which is why black holes are, well, black. Despite their reputation, black holes aren't exactly cosmic vacuum cleaners. They don't go around sucking up everything in sight. If the sun were replaced by a black hole of the same mass, don't worry, it won't be. Earth would continue orbiting just as it does now, only much colder and darker. What makes black holes so interesting isn't what they take, but what they reveal about space, time, and the limits of our knowledge. According to Einstein, gravity isn't a force that pulls. It's a bending of space-time itself. Picture a trampoline with a bowling ball in the center. The surface dips under the weight, and smaller objects, like marbles, roll toward the center. A black hole is like replacing that bowling ball with an object so dense it rips right through the trampoline. Time also behaves strangely near a black hole. The closer you get, the slower time passes for you compared to someone far away. This isn't science fiction. It's a consequence of relativity, confirmed by experiments. In fact, astronauts orbiting Earth age slightly slower than people on the ground due to this effect. In theory, near a black hole's edge, time could slow down so dramatically that an hour for you might equal centuries for someone else. This mind-bending idea even inspired the plot of the film Interstellar. And yes, physicist Kip Thorne made sure they got the science mostly right. In the 1970s, physicist Stephen Hawking added another twist. Until then, black holes were thought to be truly black, letting nothing out. But Hawking showed that black holes can actually emit radiation due to quantum effects near the event horizon. This radiation, now called Hawking radiation, means black holes can slowly lose mass and eventually evaporate. Yes, black holes can die, though it would take longer than the age of the universe for one the size of a star. This discovery was revolutionary. It suggested a link between gravity, quantum mechanics, and thermodynamics, three areas of physics that usually don't play nicely together. You might wonder, if nothing escapes a black hole, how do we know they exist? Astronomers have gotten clever. We can detect the influence black holes have on nearby stars or gas clouds. In 2019, the Event Horizon Telescope gave us the first direct image of a black hole silhouette, a glowing orange donut surrounding a dark shadow 55 million light-years away. Even more dramatic are gravitational waves, ripples in space-time caused by black holes colliding. These were predicted by Einstein, but only detected in 2015. Despite all we've learned, black holes remain one of the greatest enigmas in physics. What happens inside the singularity? Does information get destroyed there, violating the rules of quantum mechanics? Could black holes be hiding wormholes or pathways to other universes? We don't have all the answers yet. But with new telescopes, supercomputers, and brilliant minds probing deeper into the cosmos, we're inching ever closer to solving the puzzle. Until then, black holes continue to teach us something profound. Sometimes, the darkest places in the universe hold the brightest clues about how it all works.